The next problem is 4.75. Here I have a little sketch of the problem. On the side, I already drew the control volume and the points of interest, so point 1, 2, and 3. And the control volume goes around there. I also drew the normal vectors pointing out of the control volume, so that's with the little n hat, and also my coordinate system that I defined for this problem, so x and y up on the top in black. The next step, as always, is to start with the conservation of mass. So here we know that the equation is going to be 0 is equal to the rate of change of the mass inside of the control volume plus the ingoing and outgoing fluxes. Now, because we're at steady state here, the rate of change of the mass inside the control volume is going to remain constant, so that'll be 0. And what we're left with is 0 is equal to rho v2 minus 1 because of that normal vector a1 plus rho v2 a2, and then again rho v2 a2 because we have two of those, one on the top and one on the bottom, and then again plus rho v3 a3, which is going to be the output. Now, because we're assuming the densities is remaining constant and also the velocity is remaining constant at 5 meters per second here, we could find an expression for the area at 2 dependent of the area at 1 and at 0.3. The next step here is to do the conservation of momentum. So we know that the summation of forces is going to be equal to the rate of change of the momentum inside the control volume plus the ingoing and outgoing fluxes. Again, because we're at steady state, the rate of change of the momentum inside the control volume will stay constant, which means over time it will be 0. Now here what I'm doing is that I'm just indicating where I pose my reaction vector. So I'm going to suppose that Rx is going to be in the positive x direction. One thing of note is that there is no reaction force in the y direction. We can prove it on paper, but just looking at this problem intuitively, we know that the only force that's going to be generated is from the outgoing momentum in the y direction at point 2. And because they are at the same angle, they will be opposite and equal, which means they will cancel out and there will be no reaction force in the y direction. Now we can rewrite the momentum equation as being Rx is equal to rho v minus 1, again because of the normal vector n hat, a1, plus rho v squared a3, so that's the outgoing flux. And then we have minus rho v2 a2 sine theta, and then again minus rho v2 a2 sine theta. Now it's important to note that the negative there comes not from the normal vector, which is going to be positive n hat, but because the flux is going in the negative x direction according to the system of axis that I posed at the start of the problem. Now what's left is that we could find a final expression for Rx in terms of all these known variables. All right, so here I am. I loaded up Octave here on the other screen. And what we're going to do is just the last little part of the question. Last little part of the question just asks to plot it from 0 to 90 degrees right here. So we found the expression earlier for the reaction force in X. Again, the reaction force in Y is going to cancel out due to the symmetry of the problem right here. So no matter what the force is going to be coming out of this way, it's going to be equal and opposite in this direction, so they're going to cancel out. So the first thing to do here, we're going to write down all the kind of variables we need. So we need rho, which is the density of water. Is the problem with water? Yeah, it's with water. So we'll say 1,000, semicolon, not to output. And then I'm just going to write the units, so kilogram meters cubed. Next we have the velocity, so v is going to be 5 meters per second. And then we have the areas. So we don't actually have the areas, but we have the diameters here. So I'm just going to do big D is 0.1. And again, this is going to be in meters. It's in meters, and the little d is going to be 0.025. Again in meters. Semicolon there. And next is going to be, so we need the areas. So area 1. Area 1 is defined by the bigger diameter here, so we're going to do pi times bigger diameter 1 squared. I'm just going to do times 2 divided by 4. So this will be in meters cubed squared. And then for the area 3, right here, we just change the diameter. This, and then if we run it, actually I'll just clear this. So if we run it, nothing should come out. All right, that's because we commented out everything. So the next step is area 2. So we know that area 2 from the conservation of mass here is area 1 minus area 3, and that will be divided by 2, just like that. And again, this is going to be in meters squared. All right, so everything's in standard units. We seem good to go to write down the final equation here, which is Rx is going to be equal to rho times V times, and then we have minus A1 plus A3, 2 times A2 times sine of theta. What is theta? Well, theta, we can just put that is equal to 0. So now we should get, if I run this, we should get an output. If I go to the command window, we get a command right here. Rx is equal to minus 1.84. This would be in newtons, again, because we're working all here in standard units. All right, so now that we have the expression for this, the last thing to do is to just put this in a plot. So the way to do that in MATLAB is to make theta here a line space, and we'll make it vary from, so the problem asks to vary from 0 to 90. So we'll do 0, 90, so this means I want points from 0 to 90, and I'll put we'll just put that many points. It's like 1,000 points or 10,000 points. And then theta will go here in sines, which means that our output here, so if I uncomment this and run this, our output, ooh, there's a lot, but you'll see that our output for, we'll get, maybe I can put less points. Say if I put 10 points. So I run this. So you'll see theta is taking points from 0, 10. It's going to take 10 points from 0 to 90, and then we'll be able to compute our values Rx from these certain points. So we do want a higher resolution, take more than 10 points here, and we're going to comment this out so we don't get that crazy output. And the last thing to do is to just use the MATLAB command plot. So our y-axis is going to be theta, and our x-axis is going to be the reaction in x. And if we run this, we get this graph, which doesn't really look like what we're supposed to have. So if we think of the problem here, what we're supposed to have here is a reaction force, and logically the way that we would think this is that at 0 degrees here we'd have a force in x, which means we need a reaction force that's negative to hold this plate against. And then as we tilt the angle, we'd expect something to either increase or decrease. What we have right here is a sinusoidal wave. That doesn't really make sense. So what's the problem? Well, the problem is that I'm using degrees here. Now, theta here, sine takes it is in radians, which is a common mistake. So now if I replace this by pi over 2 instead, so pi over 2, that's 90 degrees. And we will rerun this. And look at that. So now we get something that makes a little bit more sense here. We start with a negative force here, so at 0 degrees, which means our plates, the plate is flat here. The reaction force that we're going to get is going to be about minus 183. And as we slowly start to increase the angle here, well, more water is going to shoot back here, which means we're going to require a greater force in the x direction, because it's going to have to oppose this momentum of fluid. So as we increase the angle, we start to get a greater reaction force in the x direction.